Hello, am I audible?
Yes,
Yes.
yes,
And can you see my screen?
yes.
Okay. So today we will see polynomial regression. So sometimes what happen, we have non-linear relationship in our data, right? So if we want to capture non-linear relationship between input and output, then we cannot use linear regression, right? Because linear regression can only capture linear relationship. So for that we will use non-linear, non-linear model, or we will use polynomial regression, right? So polynomial is a non-linear model, right? Yes. So linear relationship means uh, plane, line, or hyperplane, all are the linear model, right? So if we are learning line, plane, or hyperplane, which means we are learning a linear relationship between input and output, right? So let's say if the relationship between input and output is like quadratic, right? Then we have to learn a quadratic equation, right? So polynomial we will fit there to capture that non-linear relationship. So for example, this is an example of quadratic equation, right? Y is equal to x square minus x minus 2. So if we have such type of relationship between input and output, then we can use quadratic equations. But yes, we cannot fit here a straight line, right? If we fit a straight line, then error will be high, right? RMAC error will be high, or the accuracy will be low here, right? So error will be high if we fit a linear model, uh, but the relationship in data is non-linear, right? Yes. So then how can we fit this kind of non-linear data? So answer is simple. We can use, we can fit a non-linear model, right? Okay. Now, there are two ways to do to fit a nonlinear model. What you can do, you can yes, yes. In first method, what you can do, you can create a nonlinear feature, right? So suppose input features are given to you, right? So suppose x1 is a feature, x2 is a feature, x3 is a feature, right? So what you will do, you will use three feature given feature, right? So originally we are only having three feature in our input, x1, x2, and x3. Now using these three features, we will create a new features, right? So we will create, so depending upon what type of polynomial we want to use. So suppose if we want 2 degree 2 polynomial, then we will create the degree 2 term using given original features, right? If we want 3 degree polynomial, then we will create term 3 degree term, we will create 2 degree term, we will create, and 1 degree term we will create, right? So let's say if yes, so for linear model, what type of model we will learn here? We will learn like theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. So this type of model is linear model, right? So here you can see this is degree 1 term, right? Degree 1 term, degree 1 term, and degree 0 term. But let's say if you want to learn degree 2 polynomial, then in degree 2, we will have degree 2 term plus degree 1 term plus degree 0 term, right? Degree 0 term means bias term, right? So what we can do here, so let's say if you want to learn a uh, degree 2 polynomial, right? And for the sake of simplicity, assume we are only having two features, x1, x2, x1, x2. And if you want to learn degree 2 polynomial, then what will be the equations? So theta 0 plus, then theta 0 bias term. So here we are having degree 0 term, then all degree 1 term we will write here, theta 1 x1 plus theta 2 x2. So here degree is 1, right? So degree 0 term, then degree 1 term, then we will write all degree 2 term, right? Theta 3, let's say x1 square plus theta 4 x2 square plus theta 5 x1 x2, right? So if we want to learn degree 2 polynomial, then we will learn this type of equation, right? Okay. Now here there are two uh, there are two methods. Either you can directly learn this type of quadratic polynomial, right? So suppose this is your polynomial. Using this polynomial, you will you will calculate the predicted value, and you already have the actual value. So you will use predicted value, actual value. You will create RMSE, right? You will RMSE or MSE. You will calculate for the complete data, and then you will optimize that. Loss, RMSE or MSE loss, right? And after optimizing, you will get the optimal value of these theta values, right? So this is one method. In method one, what you will do? You will use this equation. You will calculate output, predicted output. You already have actual output. You will use predicted and actual. You will calculate RMSE or MSE error. You will optimize, you will use any optimizer, right? So you will minimize that RMSE or MSE, and you will calculate the optimal value of these theta values, right? The other method is, since these two features you already have, so you will add here some more non-linear features, right? So degree 0, right? We already have degree 1, degree 2, sorry, degree 1, we already have from linear model. So what we want? We want degree 2 features, right? Because we want to learn degree 2 polynomial. So these are the degree 2 features. So we will create here three more extra features, right? And we will add these three features, x1 square, x2 square, and x1, x2, and then we will learn a linear model, right? So both approaches are the same. You will get the same answer, right? Because here also you are doing the same thing, right? So you are treating x1 square as a new feature, x2 square as a new feature, x1, x2 as a new feature, and you are thinking like this is some new feature, let's say uh, uh, x3, right? x3, this square is, you can think x4, x1, x2, you can think x5. So it's now theta 0 plus theta 1 x1 plus theta 2 x2, sorry, theta 2 x2 plus theta 3 x3 plus theta 4 x4 plus theta 5 x5, right? So you can think that this is a linear model. If you consider x1 square as a new feature, x2 square as a new feature, x1, x2 as a new feature, right? But these features you are taking degree 2 combinations, right? So like that, if you want to learn a degree 3 polynomial, then you will add a degree 2 term, you will add degree 3 term, and then you can apply a linear model, right? Because these features, extra features we are adding, and we are considering these features as a new feature, right? And both are equivalent. Either you can directly learn a nonlinear model, or you can create nonlinear features. You can add nonlinear features, and then you can learn a linear model, right? So here it seems you are learning a linear model, but indirectly you are learning a nonlinear model, right? Because this x3 is not a linear. X3 is in fact x1 square, x4 is x2 square, and x5 is x1 x2, right? Any doubt here? So if you are learning a polynomial, then this type of regression is called polynomial regression, right? Okay. So let's test it. So what we will do, we will first create a nonlinear data, right? So to create a nonlinear data, I'm using this equation. So y is equal to 0.5 x1 square plus 1 x1 plus 2, right? So degree 0 term, degree 1 term, and degree 2 terms, so, right? So and here we are only having one feature x1, right? And y is the output and input is the x1, right? In input we are only having one features, right? So here we are adding Gaussian noise, just we did for the linear case, right? There also we added some noise, right? So we are adding this noise, and we know that this is a quadratic equation, right? So degree 2 polynomial we can fit here, right? Okay. So yes, so the code is same, right? Because same code we have used for the linear case, right? So as you can see here now, this data is having no linear relationship, right? Or in fact, degree 2 polynomial we can fit here, because we cannot fit a straight line here, right? If we fit a straight line, RMSE error. So here we will import polynomial features from scikitlearn.preprocessing, and then we will use polynomial features to create no linear features, right? To create degree 2 features, right? And include bias is equal to false if we don't want to include bias. If we want to add bias, then you can write here include bias is equal to 2, right? And then we will fit here we will input data x, and it will give us the polynomial 2 feature x1 and x1 square, right? Yes. So polynomial feature is degree d. What it will do, it will transfer an array containing originally n features into an array of factorial n plus d divided by factorial d plus factorial n number of features, right? Because it will add no linear features, right? So some new features it will add, right? So for example, here originally we are having x1, but it will also add x1 square because we are using degree 2 polynomial, right? Yes. So this I have already discussed, right? Polynomial regression is capable to find non-linear relationship, right? Where we cannot use linear models. In that case, we can use polynomial relationship, right? Because here we are adding polynomial features, so therefore now we can capture no linear relationship present in the data, right? Yes. So this I have already discussed, right? If we write degree 3, it will add degree 2 term, degree 3 term, right? So if A and B are the original features, A square, B square, A cube, B cube, A square, B, AB square. So these types of degree 2 or degree 3 term it will add, right? So extra features we will create, we will add, and then we will learn a linear model. Yes. So since now we will learn a linear model, so we will use linear regression, and then we will fit the newly created features, right? So here x underscore poly means all features. So x underscore poly will contain old features plus as well as the newly created features, right? Yes. So new features, in new features we will have all existing features plus newly created features, right? So if degree is equal to 2, then X poly will contain both features, right? Original features plus degree 2 term features, right? Okay. Then if you fit a linear model using by putting any doubt?
Yeah, sir. Where we create this XPoly object? Hello.
No, no, no. X poly here we are getting, right?
Okay. Okay.
Hmm. Because originally we are only having one features, right? We are only having x1 features, and
Hmm.
we want to fit a polynomial of degree 2. So we have to add degree 2 term in input, right? So x1 square we have to add. So for that,
Where
yes.
Okay.
We will
By
use
the
for this.
polynomial, we create x poly, then put to the linear function.
Yes, yes, because X poly will contain degree 1 features, degree 2 features,
Okay. Okay.
right? So
Right.
yes, so here this is the original feature, right? X1, and this is the newly created feature X1 square, right? Now using these features, now we have two features, right? X1 and X1 square. Now we will train here the linear model, right? So it seems like we are training a linear model, but indirectly we are training a non-linear model, right? Because in input we are having X1 term, X1 square term, right? So it's a non-linear model. Yes. So because we are not learning a linear model on original input, right? Originally, what input we are having X, right? X is the original feature, right? Using this original feature X, we are created new features, right? And new features, we are already having existing features plus newly created features, right? So X1 is already there plus X1 square, newly created features, no linear feature, right?
If my equation is the x3, then convert, I change the degree, then return back the 3 coordinate, right?
Yes, yes. In that case, it will return x1, x1 square, x1 cube. If we have if we
3.
have only one, originally we are only having one features, right? But let's say if we have two features, let's say A and B, then it will add A, it will add B, it will add A square, B square, AB term will be there. Then A square B, then AB square, then A cube, B cube. So it will add all such terms there, right? Degree 3 term, degree 2 terms in all combination, degree 1, right?
Okay.
So now, as you can see here, we are learning a linear model on newly created features, right? So if you write here X original features X, then you are learning a linear model. But since here we are using X underscore poly contain all terms up to the degree that we have already defined. So if degree 3, then degree 3 term, degree 2 term, degree 1 term, and degree 0 term, right? So indirectly we are learning a non-linear model here, right? Okay. So originally we are having x1, but we are learning a linear model using this type of data where we are having x1, x1 square. So, so this type of model we are learning, right? Where we are having degree 2 term, degree 1 term, and degree 0 term bias variance, right?
Sir, I have a question.
Yes, yes.
How we will determine, like, because if we have only one feature, then we are saying x square plus an
Mhm.
x1. But if we, is it possible to have it x cube? How will decide? Like, we'll have only the x square plus x1 and
Mhm.
the constant.
Yes, yes.
It's, Mhm.
So, in fact, if you can visualize the data, then we can decide, right? Because here this polynomial has very simple property. So, for example, degree one polynomial. Degree one polynomial means straight line, right? So, degree one polynomial or straight line is something like this, right? So straight line, how many times this straight line will bend? 0 time, right? So if we have the linear data, then we can use a straight line. This is a degree 2 polynomial. Degree 2 polynomial can bend one time, right? Can change its direction one time. So as you can see here, now from this point, it is changing its direction, right? If you take degree 3 polynomial, it will change its direction two times. So here we are changing direction one time, here we are changing. So it's a degree 3. Similarly, degree n degree polynomial will change. If you take degree is equal to n, it will change its direction n minus 1 time, right? So you can use this fact to know a priori what type of what degree of polynomial we can fit, or if we don't know anything about the data, if we don't know, if we are unable to visualize data, then what we can do, we can generally fit a very high degree term. So let's say we can use degree 5 term, degree 5 polynomial, or let's say degree 7 polynomial, and then we can use regularization to prevent overfitting, right? So for example, what you can do here, you can fit here even degree 5 polynomial, right? So if you fit a degree 5 polynomial will bend here 4 time, right? So it will overfit, the model will be overfitted to your data, right? So then what you can do, you can use regularization technique, you can use overfitting preventing technique to avoid overfitting, right? So let's say if you are using regularization, what regularization will do? Regularization will penalize coefficient of polynomial term in such a way the model now will become smooth, right? So regularization I will discuss later, but yes, what we can do in that case, we can always have a higher degree term, because we cannot, if we are taking a lower degree term, then we may not be able to capture the relationship between input and output, and then what will then happen that we will get a very poor error, very poor accuracy, right? So error will be very high if we are not fitting a correct model. So we will start with the high degree polynomial, and then we will use regularization. And regularization will penalize our model in such a way, some coefficient it will make, become to zero, so that ki model will become smooth, right?
And what are the use case of this in
Yes,
practical
so
knowledge?
yes. So practical use cases, sometimes, so let's say whenever we are having a non-linear relationship between input and output, then we can use a non-linear regression model, right? Because linear will not work here.
Sir, here one my question here is how to identify that the input or output is the linear or non-linear.
No. We will, in fact, we don't care. We will learn a degree D polynomial, and we will use regularization.
So that means we can predict in the first time कि this model is work or not.
Okay. So let's say you are fitting here. You are fitting here a non-linear. You are fitting here a polynomial, right? Now this 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 polynomial is a 300-degree polynomial, right? So 300-degree polynomial will bend 299 times, can bend 299 times, right? So as you can see here, if you fit 300-degree polynomial, it will overfit, right? It will try to fit each and every data. So let's say if you are having some data here, it will also fit that data also, right? So it will fit all outlier, all noise present in data, it will fit, right? If you fit a linear model will not work here, right? Because data. So ideal model here is the degree 2 polynomial, right? Okay. So what you can, but a priori we don't know, right? We don't know the what type of model we should use here. So what we will start with, let's say you are starting with the degree or let's say, let's take a very simple example. Suppose the input output relationship is linear, right? Even if the input output relationship is linear, uh, it will penalize. Okay, so let me take a linear example, because here if we are fitting degree 5 polynomial, then in degree 5 there will be lots of term, right? So it may confuse you. So let me take a linear example here. Yes. Yes. So suppose this type of data we are having, and here you are fitting uh, a polynomial of degree 2, right? Now, what relationship you are trying to fit here? Y is equal to theta 0 plus theta 1 x1, because we are only having one feature x1, right? Plus theta 2 x2 square, right? So here what we will do, we will put a so originally we are having one loss function, right? RMAC we are having, plus we will add some regularization term here. And that regulation term, what it will do, it will penalize these values. It will penalize theta 1, theta 2, and so it will penalize solution. It will penalize unknowns in such a way that these has to be as small as possible, theta 1, theta 2, right? So even if you are having, let's say, y is equal to theta 0, theta 1 times x1, and let's say this the regularization is penalizing theta 2 in such a way that value of theta 2 is, let's say, 10 raised to power minus 7. So 10 raised to power minus 7 times x1 square, right? So since this coefficient is very small, so this term you can neglect, right? This term is, so indirectly you are learning a linear model, right? So it's not a non-linear model because this higher order coefficient is very small. It tends to 0, right? And why it is tends to 0? Because optimizer will penalize this coefficient theta2, right? Because this theta2 is not required for this data, right? So it will penalize theta1, theta2, but yes, it cannot penalize theta1. If it penalize theta1, the error will be increased. The error will get increased, right? So to prevent this case, it will only penalize theta2, right? So using regularization, we can fix this problem, right? Because here a priori we don't know. So if you visualize this data, then because since it's a toy example, you can easily identify that a linear model will fit. But in general, let's say you don't know anything, then you can start with the higher order polynomial, and you can use regularization. Regulation will penalize higher degree coefficient in such a way that these higher degree coefficient will become very small, right? If they are not needed, right? So, for example, in this case, theta2 is not needed, so theta2 will become small. So it's a job of regularization to make theta2 very small, right? Any other doubt?
If let's say we have a degree 2 polynomial, so there is one option that we start with linear and then go to degree 2.
No. Then you have to search several models, right? You will train multiple. So that option you can also try. You can start with degree 0, degree 1, degree 2, degree 3, and whatever model is giving the best performance, you will choose that model.
Yeah, so my question was exactly that if let's say we train a higher degree model, let's say degree 5, we start with degree 5, then the cost of training such a model will be higher because the calculation will be more complex.
Yes. So then you can use the second approach, right? You can directly train higher order degree term, but just use the regularization term. Regularization will automatically penalize higher degree coefficient.
So is it better to start with higher degree and then come down, or start with lower and then?
No. We don't care. Higher degree coefficient will become automatically 0 if higher degree terms are not required.
So in terms of training cost, which approach works better?
No, if you are considering only one model, then definitely, right? If you only have x1 term, then calculation will be easy. If you are having some more extra term, x1 square, x1 cube, then that will increase our computations, right? So that will slow down our model, right? But if you are searching 100 model, then selecting one model, and other case you are adding some extra features and using regularization, then definitely the training time will be less as compared to training 100 model, right?
Okay, so how do you decide what degree to start?
Generally, people start 5-7 degree term because rarely we will use 100 degree, 200 degree polynomial, right?
Okay, so you can start with around 5 and then use regularization.
Yes. But actually, we don't know anything about data if we are dealing with the high dimensional degree data. So then we will use cross validation, right? So again, we will try some random degree polynomial. So for example, 10 degree, you can start. So let's say if using 5 degree or 3 degree, you are getting best performance, you can stop there, right? Because uh, it depends on how much error you can tolerate, right? If using, let's say, you have tried degree 5 polynomial and error is below that what you can tolerate. So let's say if epsilon is the your criteria, that error has to be less than epsilon, and if you are getting less than epsilon, you can stop there, right? But if you are not getting, then we have to try other options also, right? Because if you are using degree 5 polynomial, but let's say you really want degree 100 polynomial, then regulation will also not work there, right? Because regulation can only come down degree 5 to lower degree polynomial. It cannot increase the degree, right? So then we don't have any options, and we have to try several other possible options also, right? So you will try degree 5, you will try degree 10, you can try degree 20, right?
Practically, most of them will fit around degree 5 to 7. That's what you're saying with regularization.
Yes. No. So regularization will automatically reduce the degree of the polynomial that we are starting, right? But why are not we starting with the degree 100 polynomial or degree 200 polynomial? Because if you are taking degree 100 polynomial, then it will create so many features. It will add so many features to the original number. So originally, let's say we are having 5 features, it will add so many terms in our data, right? So then the training or testing will become very slow, right? Okay. So here, let's say if you add degree 2 polynomial term, then you end up learning this type of model, right? Now, this 0.56, 0.93, and 1.78, these optimal weights we will get using optimizations, right? So either directly you can, so you will use some optimizer, you will minimize MAC, or so let's say if you are taking MAC loss, so MAC loss will be minimum if you use these values 0.56, 0.93, 1.78, and it is same just we did for the linear case, right? Okay, so finally you end up learning this type of model, right? So it's a degree 2 polynomial, and as you can see here, if you fit degree 2 polynomial, then error will be okay. So any doubt here? So even if you fit here degree 3 degree 3 polynomial, directly you cannot use degree 3. You have to add regularization term also, right? Because if you fit degree 3, degree 3 will bend. So what happens, let's say even if you are using x1 cube, the coefficient has to be very small, right? So then what happen, that the model will become smooth, right? So in regularization we will do exactly, right? So regularization I will cover. So there we will see higher order term, it will penalize, right? Regulation will penalize to prevent overfitting. Okay, so let's now discuss learning curves. So in learning curves, what we do, so higher degree polynomial fit the training data much better than the plain linear regression if we are having no linear relationship, right? Because we cannot capture no linear relationship using linear models, right? So we can fit a so let's say this example. In this example, we are fitting a degree 1 polynomial. Degree 1 means line, straight line. Degree 2 polynomial, right? Parabola, and degree 300 polynomial. So as you can see here, this 300 degree polynomial clearly is overfitting, right? Because here this 300 degree polynomial is trying to fit every point, every data points, right? Okay, so here the correct option is to use the degree 2 polynomial, right? Okay. So plain model, degree 2 polynomial and degree 300 polynomial, right? Okay. So as we can see in previous diagram that um, uh, that the 300 degree polynomial trying to fit each and every data points, and will also fit model noise present in the data. So it will create a overfitting problem, right? So high degree polynomial model is severely overfitted to the training data, and the linear model is underfitting, right? Because this model is too simple, right? So here, so underfitting, overfitting, I've already discussed, right? So if you use linear model here, underfitting will happen. If you use the 300 degree polynomial, overfitting will happen, right? Right? So underfitting means when the training error is also high, and the test error is also, test or validation error is also very high, right? So both training and testing error are high in case of underfitting. In case of overfitting, training error is low, but the test or validation error is high, right? So since this 300 degree polynomial is fitting each and every point perfectly, so therefore training error will be less, but this model is clearly is not generalizable, so test error will be high, right? So here, if you use 300, it will create overfitting problem, right? And this, for this linear model, even this model cannot fit the training data very well, right? So if you use this linear model, training error will be high, test error will be high, right? Okay. So now the question is, how do we find model is overfitting or underfitting underfitting the training data? So you can simply calculate the training error or the testing error, and you can use the cross validation to calculate to decide whether whether underfitting or overfitting is there or not, right? Okay. So what we will do, we will yes, and conditions I have already discussed, right? So if model performs well on the training data, which means the training error is very less, training error is very less, or the training accuracy is very high, training performance is very high, but the test error or the test performance or validation performance is poor, then a model is overfitting. Overfitting means we are using too complex model. Data is not that much complex, and we are using too complex model. So, for example, here, right? So, data is not so complex, and we are fitting here 300-degree polynomial, right? Underfitting means model is too simple. So, let's say this quadratic relationship we are having originally, but we are fitting a very simple model. We are fitting a very basic model, right? So, so that will result in underfitting problem, right? So underfitting means model is too simple. If you use too simple model, underfitting will be there. If you use too complex model, then overfitting will be there, right? And we will use training accuracy. We will use validation or test accuracy, or you can use error also, right? Training error or test or validation error to check whether overfitting is there or underfitting is there, right? Yes. So another approach is to use the learning curve, right? So first approach is we can use cross validation. So cross validation we have already discussed, right? So you can use cross validation to know to calculate to know whether underfitting is there or overfitting is there. The other option is we can use learning curve. So learning curve means we will plot model performance uh, on training set and validation set, right, as a function of training set size. So what we will do here, x-axis we will take variable training set size, right? So for example, let's say originally we are having 100 training points. We are having 100 training points in our data set. What we will do, we will only pick 10 points and train model. We will pick 20 points and train our model. We will pick 30 points out of 100 points, and we will train our model. So likewise here we will create we will choose variable number of training points, and we will train our model, and then we will create training performance and the validation performance. So we will draw this curve, and this curve is called the learning curve, right? So learning curve are nothing but the plot of model performance, right, on the training set and validation set as a function of training set size, right? So here we are plotting as a function of training set size, right? So originally, let's say assume we are having 100 training data, and we are randomly selecting some data points, and we are calculating validation accuracy or training performance or validation performance. So this type of plot is called the learning curve, right? Okay. So to generate a learning curve, we will simply train the model on different sized subset of training set, right? So we will plot learning curve. So here, let's say if the problem is we are solving a linear regression model. So for linear regression model, if let's say we are having originally having 100 training points, and if you pick randomly, and if you calculate training and validation performance here, so you will get this type of curve, right? So this curve is a learning curve. Now, using this curve very easily, you can calculate overfitting or underfitting, right? So how can you calculate underfitting or overfitting if you are given this type of learning curve? Can you answer? So RMAC is a error. RMAC is a error, right? So if overfitting is there, then what will happen? So this red means the training error, right? If overfitting is there, then training error will be small, right? Training error will be small. and validation error will be high. And if underfitting is there, then training error will be high. At the same time, test error will be high, right? Okay, right? So for, let's say, if we are having underfitting, then training as well as the validation, both error will be high, right? If we are having overfitting issue, then training error will be low and validation error will be high, right? Okay. So let's say if you are doing linear regression, if you are training linear regression model on different training set size, and if you plot curve, right? So so now let's visualize this learning curve. So here when we are only having very few instances, for example, only one or two instances in the training set, then model can perfectly fit them, right? Model can perfectly fit them if we are having only very few instances are there, one or two, right? Okay. Yes. So first of all, here we are learning a linear regression model, which means we are learning a linear model, right? Okay. Now assume you are only having one data point. Now this one data point you can fit any line, right? So this line also fit this data point. This line also fit. So in fact, there can be infinite many line using which you can fit this one data point, right? So that's why the training error, right? So training error is zero, right? Because perfectly you can fit one data point using any straight line, right? That passes through that point, right? So this line also pass through this training data point. So training error will be zero. You can also use this line, right? But the validation error will become very high because here using one data points we cannot predict a line, right? Okay. So when there are just one or two instances in the training set, the model can fit them perfectly, which means the training error here is very less, right? But at the same time, we will have a high validation error, right? Okay. Yes. But as you add more and more data point to the training set, it become impossible for model to fit the training data perfectly, right? So if you are adding more and more data points, let's say you are adding more points, right? So now a linear model cannot perfectly fit all these data points, right? Even let's say we are using this linear model, so there will be some error, right? So now it cannot fit uh, training data perfectly. So as you can see here, if we are increasing number of data points, if we are increasing number of data points, the training error is increasing, right? But at the same time, this validation error is decreasing, right? Because now we are sure that this can be the line, right? Because if we are having so many points, then definitely we can say that the model has to be in this direction, right? If we are only having one single point, so let's say we are only having this point, right? Now for just using single point, uh, infinite many line can fit here, right? So this line will also fit, this line also fit, this line can also fit, right? This line can also fit. So that's why we will have a very high validation error when we are having only few data points. But as you add more and more data point, the validation the validation error will decrease, right? Because now we know that this can be the optimal model, right? Yes. So yes. and the error on the training data goes up until it reaches a plateau, right? So as you can see here, the training error now has stabilized, right? The validation error is also stabilized, right? So now after this point, if you even if you add some more data points, um, uh, it will not change, right? So at that point, adding new instances to the training set, if doesn't make error much better or much worse, then we can stop at that point, right? So for example, here you can see even after after adding 70 data points, even if you add some more data points, you will get similar kind of trend, right? Yes. So this slide I have already explained, right? So if we are having very few data points, then we cannot calculate the correct model. So then the training error will be less, but at the same time validation error will be high. Or in other word, model generalization performance will be very poor. Generalization performance means the training time model is doing perfectly fine, but the test time or the future time model is not doing so good, right? Which means model is not generalizable. Model is not generalizable to the for the future data, right? Yes. Yes. So this slide also I have already explained, right? So as we add more and more example, the validation error will reduce, right? Yes. So this point, uh, after let's say 20 data points, 20, 30, 40, 50, 60, 70, and 80, right? Both curve has reached a plateau, right? Because they are close and RMSE error is fairly high. So now you can say that here what problem we are having, underfitting or overfitting, right? When you have very less number of data points in your data, then we cannot say anything, right? So we have to have sufficient number of examples in data, then only we can say that this is an underfitting case or overfitting case, right? So clearly these learning curves are example of underfitting. Why underfitting? Because we are having high training error and high validation error. So both error are high, right? So this means we are having underfitting, right? So we are model is too simple. So then what we will do here? We will increase model complexity. We will use here non-linear model, right? Hello, am I audible?
Yes, sir,
Yes,
you
sir.
are.
Okay. So if model is underfitting the training data, then what we will do? We will use non-linear model. And how can we use non-linear model? So either directly you can use a higher degree. So if you are using regression, then you will use polynomial regression, right? Or if you are doing classification, then you will use or more complex model, right? So linear model is simple model, so you will use non-linear model to increase model complexity, and that will fix this underfitting issue, right? One point here you can note that even if you add data point, even if you increase data point, increasing data point will not fix underfitting issue, right? Increasing or adding more data point to your data set will not fix the underfitting issue, right? So as you can see here, when we are having 30 data points in our data set, still we are having high validation error, high training error, right? If we have 50 data point, then again we are having high validation error, high training error. So we are adding more and more data points to our data set, and still this problem is not fixed, right? Still we are having high validation error, high test error, right? So adding more training data will not help if we are having underfitting problem in if you are fitting here. So if you fit if you fit here let's say a linear model, let's say if you are having very few data points, again let's say if you are having very few data points, again the will be nearly equal to the 0, but the validation error will be high, right? Because if you have one data point or two data point, right? So let's say if you want to fit a straight line, so to know the correct straight line, at least okay, at least two data points has to be there, right? Let's say if these two data points we are having, then we can say that this can be the straight line, right? Or let's say if we are having these two data points, then we can say that this can be the straight line, right? Similarly, for degree 3, at least 4 points we can have, right? So when here we are using 10th degree polynomial, and if we are having less than 10 number of data points, then lots of uncertainty will be there, right? So for example, in linear case, if you only have one data points and we have to fit a linear model, then there can be infinite many linear model that can be possible. So uncertainty is very high, right? So if we are fitting a 10th degree polynomial and we are having 9 number of data points, so for example, to fit a degree 1 polynomial, 2 points is required minimum, right? So if you have less than 9 number of points, it will fit perfectly, right? So that's why you are getting here zero error, right? But at the same time, since we are having lots of uncertainty, so maybe you are not, you will not get the correct model. So that's why the validation error is very high, right? Okay. So yes, but when you increase the number of data points, the training error will get increased, and the validation error will start decreasing, right? We are having noise in our data. We don't have the perfect relationship in our data set. So that's why some error will be there, some training error will be there, right? So as we increase the data, it will the training error will get starts increasing, and the validation error will start decreasing, right? Okay, so this is the point where we can stop, right? Because both has stable now, right? So this training curve is also stable, the validation curve is also stable now, so we can stop there. Now we will again check the same property. So as you can see here, the if you check the training error, the test error, you can calculate the training error and the test error, right? So which clearly shows the model is now overfitting, right? Because training error is less, but the validation error is high, right? Validation error is high, but the training error is less. So why we are having here overfitting? Because we are fitting a 10th degree polynomial. Then now how can we fix it? We can fix it by decreasing model complexity, right? We can decrease model complexity uh, to fix this problem. Or you can use outlier detection algorithm. You can use pre-processing technique to fix the data, right? Okay, so and yes, this slide I have already discussed, right? If we want to increase, if we want to reduce bias, what we will do? We will increase model complexity. But increasing model complexity increases variance, but at the same time reduces its bias, right? Conversely, if you reduce model complexity, reducing model complexity will reduce um, variance, but at the same time increases its bias. So that's why we are having trade-off between bias and variance. right? So bias means underfitting. You can think like underfitting. Variance means overfitting will be there, right? Okay. So any doubt in this slide? Okay. Okay. So now let's discuss regularize linear model. How can we regularize um, linear model? In fact, we can do regularization model, non-linear model also, right? So it's not like that we can only regularize linear. In fact, any model we can regularize, right? Yes. So this regularization we generally use to reduce the overfitting problem. To reduce the overfitting problem. So it is hard for a model to overfit the data if it has the less degree of freedom, right? So less degree of freedom means if you decrease the degree of polynomial, which means you are decreasing degree of freedom, right? Because degree 1 can only bend 0 time, degree 2 can bend 1 time, degree 3 can bend 2 times. So like that, if you decrease the number of degree of polynomial, number of degree of freedom you are reducing, right? Yes. So what exactly we will do here in regularization? So suppose if you are learning a degree 4 polynomial, and for the sake of simplicity, assume we are only having one feature x1. So we are learning a function of something like this: theta 0 plus theta 1 x1, theta 2 x1 square, theta 3 x1 cube, theta 4 x1 4. So this function we are learning, right? So here in regularization, so we will use here some laws, right? The laws can be anything. So let's say if you are using MAC law, MAC laws, what MAC laws will exactly do? MAC laws will so let's say in MAC laws we will have actual value, we will have predicted value, uh, we will we will calculate this difference actual minus predicted square, we will sum it for all training example, then we will divide, right? So suppose if we are having m number of examples, so we will sum this for I is equal to 1 to m, we will calculate this actual minus predicted for all training points, and then we will divide by m, right? So this is the error that we will use, MAC error, right? Formula I have already we have already discussed, right? So MAC error, let's say you are taking here. So we will add here one more term, regularization term, right? And this regularization, what exactly will do? Regularization will penalize these coefficient, right? So it will penalize theta 1, theta 2, theta 3, theta 4 in such a way that if theta 3 is not required, it will become very, very small. If theta 4 is not required, theta 4 will become very, very less, right? Okay. So in case of, let's say if you are taking MAC error, then what exactly we are doing? We are trying to estimate, we are trying to calculate, we are interested in calculating optimal theta 0, theta 1, theta 2, theta 3, and theta 4 in such a way we want this MAC error as low as possible, right? That's exactly what we are doing here, right? So we are calculating theta values that results in lowest MAC error, right? So we are solving here minimization problem. We are solving here minimization. If we want to add here some more conditions, so there can be several methods for regularization. So one simple method is you can take here the absolute values of these theta, theta 1 plus theta 2 plus theta 3 plus theta 4, right? So if you take absolute values, this type of regularization is called L1 regularization. Why L1? Because we are taking here L1 norm of these theta values, right? So in case of L1, we will have this type of function, summation theta I, right? So this type of regularization is called L1 regulation. The other regularization is L2 regularization. In case of L2, what we will have? We will have here L2 norm. We will have here L2 norm, theta 1 square, theta 2 square, theta 3 square, theta 4 square, right? So since we are taking here the square term, summation theta I square, so this square is nothing but the L2 norm, right? So this type of regularization is called the L2 norm, right? So this is the L1 regularization. If we are taking L1 norm, if you take L2 norm for these unknowns theta 1, theta 2, theta 3, theta 4, that type of normalization is called the L2 normalization, right? The important part here is this: what exactly we are doing here? We are minimizing MAC loss, right? So we are minimizing. Now we have added regularization term in our loss function. So now we have to minimize. We have to minimize these two terms simultaneously. MAC error has to be low, and this regularization error has to be the low, right? Because what exactly we want? We want this sum to be the minimum, right? So when can this R regulation term can become small? When these values are small, theta 1, theta 2, theta 3, theta 4 are small, right? Because we have added magnitude of this theta value in this regulation term, right? Either you can use L1 norm or you can use L2 norm, right? But we have added magnitude of these theta 1, theta 2, theta 3, theta 4, either in L1 form or L2 form, or by using some other any other distance matrix you can use here for regularization, right? Okay. And this summation or this summation will be small when these theta values are small, right? So that's why if you have the regularized loss, it will penalize non-necessary thetas. Let's say if theta 4 is not required, then it will penalize theta 4, so that theta 4 now become very, very small to reduce this summation, to reduce this the regularization term, right? Okay. So now let me ask one question. What if I take theta 1 0, theta 2 0, theta 3 0, theta 4 0? Let's say if accept theta 0, all thetas are 0, then what will happen? Hello? Am I audible?
Yes, sir.
Yes, yes. So let's say if theta 1 0, theta 2 is 0, theta 3 is 0, theta 4 is 0, all thetas are 0, then what value we will have here for our term, regularization term? 0, right? Because here we are taking in L1 we are taking absolute value, right? We are taking here absolute value. For L2 we are using square value, right? So this square is nothing but the L2 norm, and this absolute value is nothing but the L1 norm, right? So if theta 1 0, theta 2 0, theta 3 0, theta 4 0, all are 0, then this summation will be 0, right? If you put here all 0 value, you will get 0 value, and here also you will get 0 value, right? So this regularization term will be 0. So let's say if all theta values are 0, then we will have high MAC error or low MAC error. If my data is having non-linear pattern, suppose my data is having non-linear pattern, and if I use, so let's say if theta 1 0, theta 2 0, all thetas are 0, then we end up getting y is equal to theta 1. Y is equal to theta 1 is nothing but a line parallel to x-axis. So this line cannot capture non-linear relationship, right? Because this y is equal to theta 1 is nothing but a line that is parallel to x-axis, right? If we have x-axis here, y-axis here, y is equal to theta 1 is this line, right? And if data is non-linear, suppose data is non-linear, suppose this type of data we are having, then do you think we will have a very high very high MSE error. Suppose this type of data we are having, where data is having non-relationship, right? So MSE error will be high, right? Yes. And here, what is our objective? We have to minimize this combined term. MSE plus R has to be minimum, which means even if you put theta 1, theta 2, theta 3, theta 4, all are 0, the second term is 0 and this combined term will get minimum. No. Even if you put all these theta value 0, the second term will become 0, but then the first term will increase, right? And what we want? We want this combined term to be the minimum, MSE plus R, right? Isn't it? So for that, regularization will not make all theta 0. It will only, so let's say if theta 4 is not required or theta 3 is not required, then it will only penalize theta 3 and theta 4. Why? Because let's say if you have a quadratic relationship in your data, if you have quadratic relationship in your data, then this regularization will penalize theta 3, it will penalize theta 4, right? So theta 3 it will penalize, theta 4 it will penalize, and you end up getting only 2 theta values. So then R will be minimum, at the same time MSE will be minimum, and this both MSE plus R, if you sum these two terms, you will get the minimum value, right? So see, R is not minimum, right? Because you have theta 1, theta 2, but the summation has to be the minimum, MSE plus R, right? So if we are having a quadratic relationship in our data, then regulation will penalize theta 3, theta 4, right? Yes. So for linear model, regularization is achieved by constraining the weight of the model. Weight of the model means theta 1 we will constrain, right? Because theta 0 plus theta 1 time x, so theta 1 we will make small, right? And there are different ways to constrain weight. So ridge regression, lasso regression, elastic regression. So ridge and lasso nothing but in ridge we are L2 norm we will take, L1 norm we will take, or in elastic net we will take both L1 and L2, right? So I will discuss ridge, lasso and elastic one by one, right? Okay. So let's understand L1 and L2 norm first. So L1, L2 I've already discussed, right? So L1 means we are taking absolute error, right? In L2 we will take squared, right? So we have already looked into RMSE error as the performance metric, and RMSE we will generally use for regression tasks. But we can also use mean absolute error. We can also use absolute error, mean absolute, and we can also and mean absolute is also called the absolute deviation, right? And MAE, mean absolute error, is particularly useful when we have outlier in our data set, right? When we have outlier, then we generally prefer um, um, MAE error, absolute error over 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 squared error, right? Because in both absolute and squared, what we are calculating? We are calculating actual minus predicted, right? So in absolute, we will take here absolute value, and square we will take square value, absolute minus predicted square, right? So if I am having outlier, so for outlier point, actual minus predicted, this number will be very high, right? Because since we are having outlier point, so outlier point prediction will be very so actual minus predicted, because that point is outlier, right? So for outlier point, this difference will be very high, right? So if we are having so many outlier and we are taking root mean square error, so root mean square error will magnify this difference, actual minus predicted, right? So let's say if actual minus predicted is 2, or let's say actual minus predicted is -2, So if you take absolute metric, then magnitude is 2 only. But if you take a square, magnitude will become 4, right? And what exactly we are doing in square error or absolute error? We are minimizing this quantity. So now model will minimize, will try to fit outlier points in such a way this value has to be has to reduce, right? Because in absolute or in square error, what we are doing, we are taking actual minus predicted, squaring it, and then we are doing averaging, right? MAC. And mean absolute error, we are using this function actual minus predicted. This absolute, we are doing summation. We are calculating actual minus predicted magnitude for all training examples divided by number of training examples. Suppose n is the number of training examples, right? So we are calculating this average quantity, right? So this is called the MAC error. This is called the mean absolute error, MAE, right? So if we are having so many, this value will get magnified, right? And what exactly we want? We want to minimize MAC or MAE. We are minimizing MAC or MAE, right? So now, if we are having outlier in our data set, MAC, high MAC will be contributed by the outlier point, right? Because since this point is an outlier, so therefore this difference will be very, very high, which means for this high MAC or for this high MAE, outlier points will contribute the most, right? So now, if you reduce this MAC or MAE, model will focus more on the outliers, because we are getting high error from outlier points, right? So if we want to reduce average MAC, we will reduce these values, right? Then only we can reduce MAC. So that's why model will now get fitted to the outlier points, noisy points, right? So we do not want this type of magnification, right? So for that, what we will use? We will use absolute error, mean absolute error, if we are having so many outliers in our data points, right? If we do not have outliers, we will use squared error, right? Okay. So this is the formula for mean absolute error, right? So here we are taking actual value, predicted value minus actual values, right? So the second term is the actual value, first term is the model predicted value, theta transpose x, or let's say if you are having linear model, or if you are having non-linear model, then also you will get the predicted value. So predicted value minus actual value, and we are taking here absolute value, right? So, and then we are doing the summation. We are summing it for all training data points. If there are m number of data points, divided by m, we are calculating here mean absolute error, right? Okay. So yes, in MAC or MAE, in both methods, we are measuring distance between two vector, or distance between predicted and actual, right? So here also we are taking predicted value minus actual value, right? Now this can be the scalar, this can be the vector, depending upon how many features we are having. So suppose if we are having 4 features, then in yi, sorry, so it depends on what type of how many. So let's say if you are solving a multi-output regression problem, in that case we may get here a vector also, right? Okay. So this is the formula for MAE. In MAE and MAC, in both we are calculating some distance we are calculating, right? So here we are taking absolute distance. In MAC we are taking square distance, right? Because there we are taking actual minus predicted square, right? And in absolute we are taking actual minus predicted absolute value we are taking, right? Predicted minus actual, and then we are taking absolute value, right? And we are calculating this absolute value for all training data points m, and finally we are averaging this term, right? So we are averaging divided by n, right? Because we are having m number of data points. So this is a mean absolute error, right? So to calculate the distance between actual and predicted, either you can use absolute function, absolute L1 function you can use square function, right? So here we are taking absolute function, right? This type of distance is called the L1 distance, right? L1 we are calculating. Square is nothing but the Euclidean distance, right? Absolute mean square error. Here we are using L2 norm, L2 distance we are calculating, Euclidean distance we are calculating, right? So we are having here I am discussing two types of norm, Manhattan norm and the Euclidean norm. So this is the Manhattan norm, right? Absolute norm we are taking here. Euclidean norm is square, right? Yes. So let's take this simple example. Suppose you want to calculate distance between point A to point B, right? Point A to point B. So to go from point A to point B, you can follow any path. You can follow any path, right? So if you are following this shortest path, if you are following this diagonal path, then you are and if you calculate this distance is called the Euclidean distance. This distance is called the square distance, right? A minus B whole square, right? So if you calculate A minus B whole square, then you will get the shortest distance, right? This distance is also valid, right? This distance is also valid, but here the difference is we if we can only travel along the orthogonal city blocks, if we only travel the orthogonal, then the type of distance is called the Manhattan distance, right? So for example, here you can see if you are moving in this direction, now you can only change direction orthogonal to the previous direction, right? So the orthogonal direction is this. Orthogonal direction means 90-degree angle. There has to be the 90-degree angle, right? So this type of distance is called the Manhattan distance, right? Here also we are moving in orthogonal direction, right? Suppose this is your direction. You can only change direction orthogonally, right? So if you want to change your direction orthogonal 90-degree, with 90-degree you will change your direction. Now if you want to change your direction 90-degree, you will change your direction. Likewise, you will move. Here also, if you want to change your direction with the 90-degree, you will change your direction, right? Okay. So the red, yellow, and blue paths are nothing but you are taking Manhattan distance, L1 distance you are taking. If you are following this green path, then you are taking L2 distance, right? Okay. So in L1 norm, we are computing absolute value. Mean of absolute error corresponds to L1 norm, right? Because here we are taking absolute value, modulus value. So for example, L1 norm of 2 is 2. L1 norm is 5 is 5. L1 norm of minus 5 is also 5, right? L1 norm is, let's say, minus 4 is 4, right? Because here we are taking absolute value. And for L1 norm, we will use here a symbol 1. So this 1 is 4. We are taking here L1, right? And this L1 norm is also called Manhattan norm, right? Then we have L2 norm. L2 norm we are taking square term, right? So for example, root mean square error, sum of square error corresponds to L2 norm. And for L2 norm, we will write here 2, right? So if we are writing here 1, which means we are taking L1 norm. L1 norm means absolute values we are taking. So mean absolute error, we use L1 norm, right? So this path we are taking L1 norm, right? If you are taking this green path, then we are taking here Euclidean distance, L2 distance, right? Yes. Or if we are not mentioning anything here, then the default option is we are taking L2 norm, right? So default option is here the L2 norm, right? If we are not writing anything here, then which means by default option is Euclidean norm, L2 norm, right? Okay, so this L2 norm is also called the Euclidean norm, right? So in mean absolute error, we are corresponds to L1 norm. RMSE error or root mean square error corresponds to the L2 norm, right? Yes. We do have several other norms. So, for example, L0 norm, L infinite norm, but mostly we will either use L1 norm or L2 norm, right? So this is the formula for LK norm, right? So, and yes, L0 just gives the cardinality of a vector, right? So number of elements. So suppose if we are having k number of elements, then L0 norm will give the k. So L0 norms will gives the cardinality of vector. Similarly, we have L infinite norm. So L infinite norm give the maximum absolute value in a vector, right? So in a vector, we are having several scalar terms, right? In a vector, we are having several smaller terms, and it will give the maximum absolute value in that vector. So let's take one example here. Suppose you are having vector of -5, 1, 2, and let's say 0, right? Now, if you write here L0, what L0 will return? Will return the cardinality of this vector. How many elements are there in this vector? 1, 2, 3, 4. So L0 is 4. If you write here L infinite will return the maximum absolute value in this. So the maximum absolute value is 5, right? Yes. Yes. So this fact I've already explained, right? Because if we are having outlier in our data, in outlier, since in RMS error we are using scale term, right? We are using scale term, so that's why it will magnify the effect of outlier, right? So if we have outliers, then we will prefer absolute error. If we do not have outlier, then mostly RMS error perform very well, right? So we will use RMS error there. Yes. Now, either you can use L1 regulation or you can use L2 regulation. In both cases, you can prevent overfitting. The only difference is in L1 norm, you will get a sparse solution, right? What I mean by sparse solution. So yes, so let's say you are taking MSE error. You are taking MSE error, MSE plus regularization term. Now this regularization term, for this R term, you can either take absolute error or you can take square error, or in other words, you can take L1 norm or L2 norm, right? If you are taking L1 norm, then here what I will write, theta 0, theta 1, theta. So suppose if I am having these unknown, theta 0, theta 1, theta 2, and so on. So theta 0 is bias term, and then we can have theta 1, theta 2, and so on, right? So I will write here theta I is equal to 1 to let's say 1 to n, if I am having n number of unknown, right? Right. So as you can see here, what type of norm I'm taking? I'm taking L1 norm or L2 norm? L1. I'm taking L1 norm, right? So this is called the L1 regularization. If I take here summation I is equal to 1 to n theta I square, then since I'm taking here L2 norm, so this is called the L2 normalization, L2 regularization, right? Okay. Now, if you see the form of this function, so we already know the y is equal to mod x graph, right? Y is equal to mod x. So if you plot y is equal to mod x graph, this is the y is equal to mod x graph, right? Y is equal to x square, we also know, right? This is the y is equal to x square. Right. So here we are taking L2 norm and here we are taking L1 norm, right? So as you can see here, if we minimize this L1, then this point is the minimum point, right? Here, this point is the minimum, right? So as you can see here, it will make values perfectly zero. L1 norm will make values perfectly zero because due to the shape of y is equal to mod x, right? But here, values will become very, very small, but not exactly zero in case of y is equal to x square. So that's why if you are using this type of regularization, it will reduce theta I. It will make theta I very, very small. But here this theta I will make it can make perfectly zero, right? So that's why the L1 can yield a sparse model, while L2 does not, right? Here you cannot make any theta I perfectly zero, right? Okay. So since here you can make theta I 0, and what we will have here in what model we are learning here? Model is something like this: y is equal to theta 0, then theta 1 time feature 1, theta 2 time feature 2, theta 3 time feature 3, theta 4 time feature 4, and so on, right? Let's say theta n time xn. Suppose if I am having xn feature. So now let's say if theta 2 is 0, theta 4 is again 0, which means in the model I don't have feature 2 and feature 4, right? Because theta 2 is 0, theta 4 is 0, which means originally even if I have x2 and x4, in the final model, x2 and x4 are not contributing anything because theta 2 is 0, theta 4 is 0, right? So what exactly I'm doing here? I'm not relying x2 and x4 feature. I'm not dependent on x2 and x4 feature because theta 2 is 0, theta 4 is 0. So indirectly what I'm doing here, I'm selecting features. I'm selecting important features, right? So x1 feature is important, so that's why theta 1 is non-zero. x3 feature is important, so that's why theta 3 is non-zero. x2 feature is not required, x2 feature is redundant, x2 feature is, or let's say you can think x2 feature we don't require, right? So that's why theta 2 is 0. Here also x4 feature we don't require, so that's why x4 theta 4 is 0, right? So this L1 we can also use for the feature selection, right? So which features are important? So if features are important, then we will get non-zero theta. If features are not required or redundant, then corresponding thetas will be 0, right? But here what we want? We want exact 0 value. So for that, what we will use? We will use L1 norm, right? So both L1 and L2 will fix overfitting problem. But if you want to do feature selection, if you want to make some thetas 0, then you will use L1 norm, right? And why it is possible in case of L1 norm? Because shape of this L1 is V shape function we are learning here, right? Okay, so any doubt in L1, L2? Right? Yes. So next session I will discuss L1 regulation and L2 regulation, and I have already explained what is L1 and L2, right? So very small difference is there in L1 and L2. If you use scared regularization, scared L2 norm, then this type of regulation is called the ridge regression, right? So MSE error plus this type of regularization term. In this regulation term, we are using square L2 norm. So this type of regulation is called the ridge regression, right? Yes. So as you can see here, we are having MSE error plus regularization term. And this regularization term, we are using L2 norm, right? So if we are using L2 norm, then the type of regression is called the ridge regression. If we use L1 norm, so yes, here we are using MSE error plus L1 norm, right? So if we use L1 norm, that type of regression is called the lasso regression, right? And if you use both L1 and L2, so as you can see here in MAC laws, we are having plus we are having L1 norm, we are having L2 norm. So if you are having both L1 and L2, that type of method is called the elastic, right? And why we are using this regularization term? To prevent overfitting problem, right? So we will discuss these three regularization method, raise, lasso, and elastic net next session, right?